Yes. So thank you very much. I hope the microphone works. I'm not sure. Yes? Thank you. So it's a great pleasure to be here for me for a number of reasons. Some of you might know that a long time ago I've been a postdoc here, and actually when I was a postdoc I was affiliated officially to the Newton Institute when it was had just been built. And so I was here when, this was just the field behind, and looked like the end of, the far end of Cambridge was here, and nothing was further west, or almost nothing, and this has changed quite a lot since. The other reason is, which makes this workshop quite interesting and a bit strange for me, is that, if I look at the audience, I look at the list of speakers, it looks like, I think I counted, I'm the third oldest speaker among the, bunch of speakers of this conference. So, I turned into this senior guy who is going to listen to the great stuff that his former PhD students, students of his PhD students are proving, and can sit back maybe and enjoy. Anyway, so, but then, people are having some expectation to what sort of a talk I might give, so so that's all that puts a bit of pressure. So anyway, so I really want to say that this place is quite unique in terms of, the way it is structured, the way interaction indeed, can work out really nicely, and I hope you'll all be able to enjoy it whatever time you spend here, just, and especially for those, I mean, the problem probably is that, we all know subgroups, and, if the Zurich crowd here only speaks to the Zurich crowd, and the MIT crowd only speaks to the MIT crowd, and, and then people from, it's very important that you, talk to the others. You don't know who sit around and ask what they're doing, what they're thinking about, because anybody who's around is actually very relevant to the program and to your own research, and you should, talk to whoever's there. Okay, that's just my old folks' advice. So now I want to say a few words about something that I've been thinking of for quite a while, and sort of, now with together with Stéphane Benoit and Laure Dumas, we are writing up one aspect of that, and so Laure will talk more about the actual thing that we are doing, but I will try to give you sort of the general picture, and yeah, that's it. Of course, it's a fairly wide question, a fairly wide subject. Many of the ideas that I'm going to try to present have certainly been around before. It's just the way to try to reformulate things. So it's more a personal thing that I want to try to make sense in some way, to find some sort of formalism in which I can make sense of what renormalization, some of the renormalization ideas, that are floating around mean. Say in the context of the easing model, what, the critical easing model would be a fixed point of what, right? In what space, what type of, what would be the natural conjectures that lead to that. So, okay, so maybe I'll start with just the general, if you open a book about renormalization, you might see some picture of that sort that says that somewhere here you have the continuous world, continuum. Somewhere here you have the discrete models. They might live on a lattice. You have plenty of parameters, but you're looking, say, at one model, say percolation or easing or whatever. And here you have a parameter, which is temperature or probability of an edge being open or whatever. You have sort of plenty of parameters. And the standard things type of picture we see is something like, here you have here you have P, here you have PC. And when you look at things on a larger and larger scale, then things, the lattice becomes smaller and smaller if you normalize space like this, and then basically you have a picture a bit like that, sort of where if you are subcritical, you know, quotation mark at large scale, everything, you know, everything becomes white in the end. If you are supercritical, everything becomes black in some sense. And if you start exactly at the critical point, then you end up with this this critical, you know, continuum critical point. And this guy is supposed to be a fixed point of this sort of renormalization type operation. And this fixed point is basically supposed to be unique for whatever dimension, you know, in any given model, say percolation or easing, or in any given dimension, 2, 3, or whatever, then there should be in principle a unique point that should be invariant under this renormalization argument that says, you know, look at it from further and further away, you still see the same random structure. And because of the fact that this fixed point is supposed to be unique, you would expect that indeed, you know, if you whatever discrete lattice you start with in 2 dimensions or in 3 dimensions, in the large scale, if you are at a critical point, you should converge to the same guy, right? So in some sense, this is, you know, in the physical textbooks, or, you know, the explanation to why we should expect universality to hold, why, you know, is the critical percolation or critical easing model on different lattices in 2 or 3 dimensions, why should they be the same in a very strong sense? You know, the lattice here might be a random lattice, might be a perturbation, you know, percolation, supercritical percolation cluster, whatever, should be like that. Now, if you try to you know, if you are just say a probabilist and you don't have many tools, you know that, you know, measure theory is tricky. You know, you have to we want to make this precise. So there's one instance where this type of picture has been made precise, which is the Schramm and Smirnov formalism for percolation. And you know, basically it just says the following: the renormalization type operation that you want to apply here would be to say you sample a random picture in the square, and then the operation acts on probability measures on random pictures in the square. And if you have a way to define a random picture in the square, well, then you have another way which corresponds to do 4 independent copies of the same picture, of the same experiment. So you do 4 independent experiments, each of which has this random picture the law on random pictures that you have here. And then this defines you now, again, if you look at this larger square, as a random picture on the square. Okay. And so what, and you would expect that if you're looking at critical percolation in the scaling limit, whatever that means, that if you do a picture of critical percolation at the scaling limit and you do this operation, what you get here is the same picture in distribution of critical percolation in the scaling limit. Okay. So indeed, then what Schramm and Oded and Stas proved is that indeed, if you start with critical percolation on the triangular lattice and you think a lot about what is the relevant information you want to keep in order to define what the random picture here is, say a collection of, and there's work for those of you who know the story. I know that somebody here knows this very well. You have these things, you know, you want to define this by crossing of quad events type features. But if you find a right formalism, and they had to, you know, it's a non-trivial task, they were able to prove that indeed for some, you know, right formalism, this holds, namely that there exists a fixed point of this renormalization procedure, which you can understand as being the scaling limit of critical percolation on the triangular lattice. Now, you might say, well, you could do this for any, then the question, sort of universality question, would be, well, is there another fixed point for this renormalization operation? And can you prove that basically, there are 2 other fixed points, right? One is everything white, well, then everything is white with probability 1, or everything black with probability 1. This will be also fixed points of this renormalization operation. But is there a sort of non-trivial one? And is this unique? Can you, and if so, you know, can you prove that when you start from wherever you are, you either converge exponentially fast to the discrete, to the all white, converge exponentially fast to all black, or exponentially fast to in some sense, to this critical percolation picture. Okay, so now if you try to adapt this and say, okay, let's do the same, say, for Ising. Okay? Or let's do the same in 3 dimensions, right? You could do the same, you know, random picture, whatever it means, in 3 dimensions. You have a little square, you know, a cube, and you have, you know, 8 copies of a cube. You put them together, and then you have a larger cube. Okay. But if you try to do it for Ising, where you were saying, well, I know how to sample Ising model here with, okay, what boundary conditions? Let's say 3 or 0 boundary condition, 1 boundary condition, okay? And then we take 4 independent copies, we put them together, and then, you know, nasty things start to appear because you have to, you know, they're interacting, right? So on the boundary, you have to, it's not just choosing, so the gluing operation somehow will create some, you know, singular features on the boundary, so you don't really quite know how to make sense of this type of, you know, operation in the context of Ising to start with. Okay. Okay. So now what I want to do is the following. Do the following remark. So this was sort of the global thing. I want to try to present to you some framework, you know, in which one can make precise statements about, you know, this type of picture and, you know, what the conjectures are and what we can prove. Ideologically, it's more, you know, a conceptual, trying to, you know, be more conceptually confident about what these statements that the physicists have been, you know, using might mean, rather than being able to prove something. So I'm not going to give you a recipe to prove, you know, uniqueness of scaling limit of 3-dimensional critical percolation or something like that. But what I want to say is there's a framework, and in those cases when one controls pretty well the scaling limit, one can prove aspects of universality, say critical easing in 2 dimensions. We know that, you know, various models on different graphs converge to the same thing. Whatever, you know, graph you start with, it should converge into the scaling limit to the same thing, and this is sort of, you know, actually proved. And something similar as what was going on in the percolation works, that if you could control the scaling limit of some large family of discrete models, actually you can, in this formalism, deduce that indeed there's a unique fixed point in some space, and that this and that if you start with a, you know, discrete lattice, indeed it will converge to that fixed point and sort of give some. I mean, one can state certain type of result as consequences of understanding what happened in 2 dimensions. So maybe I start with something very, you know, elementary observation. And this elementary observation is, imagine you take G, a finite graph, and so it has sides x and y, and it has edges x, well, e till xy, say, and now you want to you define these so-called Fk percolation measure Fpq of omega, and I'm sort of going to assume that everybody knows what it is. It's a configuration that for each edge on the graph is going to decide if it's open or closed, right? And it puts a mass, it puts a omega therefore as a map from the set of edges of the graph into 0, 1. 0, the edge is closed, 1, the edge is open. And this is basically going to be 1 over some renormalization constant Zg. And I'm going to write it in a slightly non-standard way. You'll see in a moment. Well, anyway, don't. So it's p to the power number of open edges, 1 minus p to the power number of closed edges, and closed in French is an f, so that's why I use f. And then q to the power, and then there's this bias, which is q to the power number of connected components, right? Sort of this connected components defined by omega. When q is 1, this is just the usual Bernoulli percolation. And I'm going to be interested here in my talk with q larger than 1, which is the case where the so-called FKG inequality holds, namely so that this model is, I mean, appearance of edges are positively correlated with each other, and on Friday law will tell you what happens, what you can say in this framework in the case of a uniform spanning tree, which is Q equals 0 or 0 plus, in which case slightly different story going on. Anyway, so we have this here. For what I'm going to say in a minute, the fact that Q is larger than 1 is not really important. You can rewrite it by no cost, just by changing the normalization constant. You can remove, k. This is just the number of sites, right? The number of connected component of the configuration which has no edges. Okay, and as you know, you can rewrite this as well as 1 over some renormalization constant, which would be different. And you could have, if you divide everything by 1 minus p to the number of edges of the total graph, it might look like pi to the number of open edges q'd k of omega minus k of empty set, where pi is p over 1 minus 1. Okay. So we know that when you increase p or you increase pi for a given model on a given graph, basically because of the positive correlation, more edges tend to be appearing, and therefore there is a natural, there are various ways to try to couple on a simple experiment all the FK models for a given Q on a given graph for different temperature in such a way that edges open one after the other. And there's a nice paper by I think Gabor, Hugo, and Christophe Gabon, who basically explained that this coupling and understanding the phase transition there in this coupling, in this movie, is far from trivial. There are many open questions there. We are, one can understand quite a number of nice things, but there are still, it's a very tricky problem to understand what happens basically when you just look at the FK model and you heat it up, progressively, the edges open, and then you get closer and closer to the critical point, and then you reach the critical point. What happens there is a tricky thing. So what I'm going to do now is something different, and it goes as follows. I'm going to choose alpha, which will be in 0, 1. And I'm going to do the following experiment. First, I sample the FK model, omega. And then for each open edge that happened to be open at the end of the experiment, I'm going to toss a coin to decide if it remains open or not. Okay. So in this way, you're going to define another guy, which I call omega tilde, which is just obtained by first sampling the FK model and then do Bernoulli percolation on the FK configuration with parameter alpha on the open edges. Okay. So you just look at this and you say, well, P, then that way you sample some guy. You have this couple here, and then, well, it's just this, and then alpha to the power. Okay, so you checked how many open edges you have for O of omega star omega tilde, right? And 1 minus alpha O of omega minus O of omega tilde. Okay. So clearly, if you now look at the marginal distribution of omega tilde with respect to this joint distribution, it's pretty complicated, right? Because you first sampled, the FK model, and then you erased some of the edges. It's a bit tricky. On the other hand, there's one very simple, trivial observation that you can make, is that what the conditional distribution of the end guy given omega tilde, right? If you write this guy, you can say, well, this is 1 over Zg, and then here you write it as pi to the number of open edges of omega tilde plus pi O of omega minus O of omega tilde, Q to the power k of omega minus k of omega tilde times Q to the k of omega tilde minus k of 0. Right, I just rewrote this guy, and then here I have alpha times O. Okay, I can put it here. and this one here. Okay, and now what you see is that this is a constant depending on omega tilde. That will include this guy, and this guy. You put it in that constant, and then we just have 1 minus alpha pi O of omega minus O of omega tilde, q to the power k of omega minus k of omega tilde. Okay? So this trivial observation just says that if I condition on omega tilde for this joint distribution, the conditional distribution of omega given this omega tilde is just an FK percolation. Okay? In the new graph, where the new graph has been obtained by, the edges of omega tilde are open, so the way you're going to count the connected components are, you're using these edges that are already open for omega tilde. And so here you're just, for all the edges that are outside of omega tilde, you're just weighting them according to this number of open edges to this power. Okay? So you have changed pi into 1 minus pi alpha, and you are using the same Q. Okay? So what I mean is the conditional distribution, what you have here, the movie is basically like this. You start this, and here I can have choosing omega. And now, we know how to erase back up to omega tilde. And what I know is that the conditional distribution, if I observe only omega tilde, the conditional distribution that remains to be, of what remains to be discovered is just an FK model in a new graph, right? Where basically you have collapsed all the edges that are open for omega tilde. And the parameter that you have here, the p, the thing that corresponds to p, has sort of decreased a little bit. So one natural thing you want to do, and of course therefore here you can do the same again, right? Starting from here, I know I have an FK model that I need to simulate up to here. So I can always say, well, I look at omega again, and now I erase fewer edges. Okay? So exactly in the same way as you would look, ordinary. So what you're doing here, the movie that you see from here, from there to there, is exactly the same movie as when you have Bernoulli percolation on a graph, and the edges appear one after the other in random order. Okay. And this is here exactly what you're doing, right? Except that your graph on which you're doing Bernoulli percolation is this FK model in, the FK guy omega. Okay. So this trivial observation seems to indicate that indeed it's a good idea to try to say, well, if you look at this picture like this, by discovering these omega tildes one after the other, here doing this, moving alpha, doing the natural increasing, coupling of all these models by increasing alpha from 0 to 1, you get a natural Markov process. Okay? So let us just think just 1 second. If alpha is very small, right here, and the graph is finite, what is going to be the configuration? Well, nothing happens, and then at some point an edge opens. What's the probability that an edge opens during the time between 0 and epsilon, when epsilon is very small? Well, it will be just epsilon times the probability that it is in omega. Okay? So in this Markov process, when you do it like this, what happens is that the rate at which edges appear or collapsing is exactly, the probability of having, of this edge being actually open in the FK model that you are considering. If you are, if you're looking at omega tilde here, and you have observed omega tilde here, what is the probability that an edge is going to open here between this just immediately afterwards? It just will appear with a rate that is that is just equal to the probability that this edge is in omega hasn't appeared already in omega tilde, and therefore that this edge appears in the FK model with probability, with parameter pi alpha and q in the graph defined by omega tilde. I hope that's pretty clear. Okay, so that's a very simple observation, and there are two things you can say. The first remark is that this, okay, one first natural thing, if you are sitting in the audience, say, well, why is he using a uniform random variable with 0, 1 and not an exponential random variable in order to have a nice Markov process? So clearly, the thing you want to do is, instead of choosing a uniformly chosen random variable here, you might want to choose for each open edge, you choose an exponential random variable with parameter 1 independently. I mean, once it has appeared, it's you choose this point with an exponential random variable, and then you define a nice Markov process. So that means that you only reach the final state omega at time infinity. The other remark is, of course, that the way I've introduced this Markov process, you can make sense of it in infinite volume as well. Because the only thing you need to do is to be able to sample omega, right, which is the infinite volume guy at the end, and then you can erase the edges. Go back and erase the edges. And so if you know that the infinite volume is, in some sense, the increasing limit of what you would see in a finite volume, then you can make sense of this business here already. Say if you start with z squared or z3 or whatever discrete graph, you can sort of make sense of this procedure. So now we see that what happens is that when you let time evolve, right, you have two phenomena that occur. First of all, the value of p on the different edges is changing; it's sort of decreasing. And from time to time, you have a jump that corresponds to collapsing, collapsing edges, meaning that you're conditioning this edge to appear. And so you need to keep track of the graph, right, and this value of p, or the time at which things happened. Now, there's a natural way to try to basically keep track of both at the same time that I just want to indicate. So everything I'm saying now is really very simple. And the idea is the following: is nice formalism, sort of, is I take a graph G, and this is going to be very important in what's going to follow. It's going to be a graph where on each edge there are weights. Roughly speaking, you should think of the sides of my graph here will correspond to the sides in omega tilde, which means that you have already collapsed each cluster has been collapsed into one side. And then there will be a weight between two sides, meaning between two clusters, which is just, how many contact edges are there between the two. So the formalism is just G, a graph, discrete graph, but you'll see in a moment we can do a bit more larger ones. And then you have, for each x neighbor of y, we define C of xy, that you can view a little bit like the conductance between x and y, of the edge between x and y. So there's just saying there's just one edge between any two sides, maximally one edge, and this edge has a certain conductance, which means somehow, if there's a multiplicity in edges, I count this like that. So you define C of xy, and so now you try to see if it's possible C of xy will already contain the information about the value of p on that edge. That's the idea, right? So C of xy will both contain the information about how many edges there are, but also some information about what the value of p is along that edge. And so you just say p of g, right? With q, so I'm going to drop q, but what is fk model of g would be now omega. So now this is a configuration on this thing, and you just put 1 over zg, and then you just do the product over all x neighbors of y of something like, okay, the edge is going to be closed with probability x. This is indicator of omega xy being closed, plus 1 minus e to the minus c of xy, indicator omega xy open, times q to the power number of connected components of omega. Okay, that's just the simple generalization of the FK model, except that you replace what I call p, 1 minus p is exponential minus c of xy. This is just because I have the idea that, you know, if c of xy in some sense counts the number of edges, if you want, you know, to be no connection between x and y, you want that none of the edges, of the multiple edges is actually open. So you get something like that. Okay, so that's what I call the FK model on G, and there's no parameter anymore. Okay. And now you want to make sense of what the Markov process is here on that, that, you know, was behind the scene here on that discrete graph. What is this Markov process? Well, you have two, you know, Markov process on G. I mean, weighted graphs, right? G is given by the information of G and C. So the first thing is, I mean, if you look at this, you say that there's, you know, P of C is just a function, you know, if you want to go back like this, is e to the 1 minus e to the minus c over e to the minus c, so it's e to the c minus 1, just a deterministic function. And so what you have is this Markov process has two features. For each x, you know, each 2 points, pi of c of xy decreases at rate 1. So which means that c of xy actually does decrease, right, with a drift that depends on the position at which you are. If c of xy is very large, it will have sort of some linear drift, and if c of xy is very small, then the drift will be roughly proportional to c of xy. So if you let the thing go, just the drift goes down, you start somewhere, you go down, and you basically converge exponentially fast to 0. Now, this is feature number 1. And feature number 2 is, well, at rate given by pg of omega xy equal 1, the edge x to y opens, means is collapsed, right? So you have your 2 points, x and y, then you identify them, meaning the edge has opened. And when you do that, the rule is just into 1. So x and y become a single site in a new graph that we call xy. And the rule is, for the new weights of the new graph, well, if you think of c of xz counting the number of, you know, edges between x and z, and that you have, the new guy will have this feature. That's the rule, how this Markov process on the graphs is going to appear. Okay? So it's very simple. If you let it go like this, nothing happens. The rates go down, they decrease. But occasionally you're going to, you know, with a rate that is given by the state of your graph at a given point, some edges are collapsed. And then what you see is that you have a very simple rule of how to construct the new graph given that. Okay. So now there's a remark that you can make immediately, that this Markov process is well defined, it's not a problem, and that indeed if you do this rule here on this discrete level, on this discrete graph that you start with, and you look at, you know, you define the graphs here that correspond to what you see when you collapse edges when they're open, then indeed if you just look at this information, it will be Markov and will follow exactly that rule. That's more or less a trivial consequence of these observations I made so far. Okay? So now what you have is a very simple, for each value of q, on state of discrete graphs, I have a unique Markov chain, you know, well-defined Markov process that can be defined like this. Now, imagine I start with a finite graph G here. Well, then this Markov process is basically doing exactly following this movie here, except that you have this formalism that you don't keep track of the geometry of where the points are, you just keep track of this collapsing graph feature. And here, this movie is not going to time 0, it's just a time chain. This is exponential. As time goes to infinity, you're going to reach this final state omega, which follows the law of the graph. Right? You choose the value of p you're shooting for to start with, which means that you choose the initial values of c's. Right? So you choose your initial graph. You have the graph G. You choose the initial values for your parameter p, and then you let this movie go, and you say you see just the edges that are going to appear in the FK percolation thing at the end, just appear one after the other, and the simple observation, which is fairly trivial, is just that this evolution, if you look at it in terms of graphs, is actually Markov. You don't need to. There's enough information in just knowing G and know the values of C of x, y's, which is just defining in order to understand this evolution. Okay, when time goes, if you start with a finite graph, then it's pretty clear what happens at the end. At the end, you have the end final configuration, so where t is sufficiently large, nothing happens, which corresponds to the fact that all the edges C, here in the finite thing, they will, eventually, some open, some don't. You only can open finitely many anyway, and at the end, basically, all the edges go to 0 very quickly. Okay, so the end configuration is some finite configuration omega with edges converging to 0. Right? Any configuration with edges equal to 0 is actually stationary under this Markov chain because nothing can happen. Okay. But again, if you start with, if you imagine that you're an infinite volume, you could say, well, okay, can I make sense of this, of this object here in infinite volume? And the answer is, well, there's no problem, right? Say, if I start with z squared, I want to apply the dynamics on graphs, starting with the graph z squared with edge given by value of p that corresponds to choice of the FK percolation at parameter p. Well, because you know that in the end, you're just, you can construct a guy in the end which tells you what this thing is at any given time. You're sort of able to say, well, I know I can define what this means also in infinite volume. Okay, even though it's clear that we're using something, but the only thing one needs is the fact that omega at time infinity, which corresponds to the FK model with parameter p, exists, and that's the only thing you need. So there's no abstract nonsense business about Markov processes and weird spaces. It's just everything is very concrete. So in the case where you start with z squared, what happens? Well, if you start with a subcritical p, you let your Markov chain run. Right? You start with the graph z squared, given with edge weights given by whatever the value of c is, such that pi corresponds to p over 1 minus pi b. And well, at the end, the process is going to freeze. It's going to converge to, well, the subcritical configuration on graphs given by omega at the end, and the value of c is going to go to 0. And this because you know that at the end nothing, the edges that are going to be open eventually, they stop being open because of the way you sampled your movie by starting at time 0 and then let the edge open at exponential times. And so this says that in the end you get basically a graph where well, all the C's in that graph locally converge to 0. All the clusters are finite. You don't have any problem. Now, if you start with a supercritical P, right, what happens is at some point you'll cross this thing where you're going to see the infinite cluster has appeared. So careful, this is the infinite cluster in the Bernoulli percolation in the cluster of FK percolation, right? You're not doing the increasing, trying to understand the scaling, near critical scaling limit movie of what happens for FK percolation near the critical thing. Here we sample we sample a supercritical FK and then we do percolation on it. But still, at some point, by 0,1 law nonsense, you will see the infinite cluster appearing. That means that at some point you will have some some site x in your graph, such that the total weights of the neighbors becomes infinite. right? So you clearly see something going on, and but still, nevertheless, locally each finite guy will actually either be swallowed in finite time with this infinite cluster, or will remain in a finite island where the C's, corresponding C's, tends to 0, the boundary up there. Okay. Now, what happens when you are at the critical point? So now I want to look at what happens when you start at the value PC here in your discrete graph. Well, so imagine so there are a couple of things I want to say. The first remark is, maybe I'll just say it, even though sometimes it's nice to say things and not write them, but here everything is recorded, so it's probably even worse. But I want to make a couple of remarks. There's the first question you may ask and say, well, what does he mean by an infinite graph which is abstract, which is not embedded, right? So here the crucial feature is that I'm looking at G here in the case of a finite graph. G is a graph, and I'm not saying G corresponds to some cluster or some point in space. I don't care, because in order to understand the evolution, I just want to get rid of all the information that is not relevant and just view this as an abstract, measure on graphs. And so you may say, well, what do you mean by an infinite graph? Is there a root, right? People with planar maps, you've learned that it's very important to know how to do this. Now, what you know is that, imagine you start with a critical FK model, or supercritical, but let's say FK. And then you erase some edges. With positive probability epsilon, you erase edges in the critical FK model. Then you'll be in a subcritical phase, where clusters size have exponential decay, right? So as long as you are in some sort of subcritical phase, the graph G you're looking at will have this side of feature that it looks more or less Euclidean, right? So in particular, there's the fact that you have exponential decay say that you will be able to have some sort of ergodicity around there, that all largest clusters will be of a certain size, typical size, and that the graph looks pretty ergodic, so that on that graph you can try to use whatever trick you prefer in order to sample a root according to some stationary measure. And so the idea will be that we are looking at these infinite graphs which are not embedded in any d-dimensional space to start with, right? But they have this sort of property that there is some transitivity ergodicity sitting behind there that tells you that there are natural ways to try to root them. Okay, we'll come back to that in a moment. Okay, so if you are at PC, so the belief, and proved in certain cases, is the following, is that if you do look at the picture near PC, so take PC and look at what omega is at PC. Because an important feature of what I'm going to say is that the fixed point we're going to get, right, is not this one. This is not the fixed point we're looking for. It is not the fixed point that's going to come out of here. The fixed point that comes out of here is, in some sense, it is exactly the generalization of to FK percolation of what Gabor, Oded, and Christophe did for the minimal spanning tree or near critical percolation features. And this fixed point will be the near critical FK model. Near critical in the sense that you sample the FK model, the critical FK model, and you erase some of its edges, few of its edges at random. Okay? So if you look at omega, right, the picture will be, let me do it in the geometric picture. You will have clusters, right? And we know that there is sort of a geometric picture like that, where the graph of clusters will be connected, okay, of large-scale clusters. Whatever scale you look at it, you see the same random picture, roughly speaking. And now what we're doing is basically we're going to erase some edges here. Now, we know that if the near critical, philosophy is that if I erase sufficiently, the exactly right amount of edges in my critical FK model, I will still see a picture of the same type. Right? I will have cut, some edges at random, except that by choosing this very small epsilon, I will get a natural scale that will correspond to that picture, namely the sort of the near critical window that says that for any little epsilon, there will be a natural scale at which I will see a certain picture, which corresponds to chopping, the critical FK clusters into smaller pieces by removing, and that's the general philosophy that sort of has been proved in some sense only in the critical percolation case by Gabor, Oded, and Christophe, that says that, yeah, if basically the only thing that happens is you remove only the pivotal points, those points that correspond to the moments where two clusters, removing that edge just disconnects two clusters. And so the idea just before PC, if you start with PC, you look at omega and then you take an alpha very close to 1, you get a picture like that with clusters that have a certain size. The largest cluster locally have a size that depends on alpha. The n goes to infinity when alpha goes to 0. Okay, and the rule of thumb is if you rescale this by the right n of alpha, the picture you see converges to some sort of near critical scaling limits of almost full FK percolation cluster graph. Okay, so what you get here is that okay, maybe I should. So what you know is that this n is going to, when alpha goes to 0, this n grows. That means that if you look at the picture and you let alpha grow, even if alpha, however big alpha, close to 1 alpha is, you let the movie continue to evolve, you'll still see stuff merging. Right? Because you will see some of the big clusters that have size n will coalesce into larger things and larger things and larger things in order to create the clusters that are critical at the critical temperature, the critical clusters of omega that appear to be there at any scale. So this means that the corresponding, C here in that movie doesn't go to 0. Right? The C's don't go uniformly to 0, otherwise the clusters will not continue to merge in the movie. They don't go to infinity either, right? So they will sort of continue naturally to merge into each other if you look at it at the global scale, at the sort of global picture on this graph. Okay. So the idea is what you see is a picture that becomes self-similar, in picture. And the evolution, right? If you look at this at time alpha or time alpha over 2 or time alpha over 4, the movie you see, is sort of coalescing movie that you get there, is actually almost always the same up to rescaling. So what does this mean in terms of G, or a graph G? You think about it in a second and say, well, it just means that G converges to a stationary distribution. Right? So that means, so in our context, if you start with G, right, please say Z squared, and PC, so keep defining C of xy, and then you let that, so G0, this is G at time 0, you apply this Markov process, what you get is G0 converges in distribution to a stationary, which is non-trivial, and that you can describe. So how do you describe the stationary distribution? Well, it's the object that you get if you know what the scaling limit of FK percolation is. If you have the natural measure sitting on the 4-arm pivotal events, exactly like Gabor, Christophe, and Oded did in the case of critical percolation, if you can control this, in order to control this, you need to control 4 arms events at critical temperature for FK. That's basically what you need. So you need to control how many there are. If you can control this, then the stationary distribution is going to be the guy that will be obtained by sampling the critical FK, then chopping, erasing some, in a Poissonian way, some of these pivotal 4-arm guys in the critical FK cluster. Okay. This defines you clusters, which are the sites of this graph here. And what is the edge weight between two clusters? It's basically the natural renormalized number of touching edges between the two. Okay. So C of xy will be the natural, renormalized naturally by the, this thing. So there are two things I want to emphasize. The first thing is that the sort of near critical window, you don't really need to, when you write this like that, it's just, there's no natural intrinsic renormalization that you need to apply, right? The belief is you start from here, naturally this Markov process will sort of, if you look at this backwards and see these sides that coalesce here, what clusters do they correspond to? What's the size of these clusters? Well, then you will see that there's natural n of alpha coming out there, right? But you don't need this n of alpha in order to define this. It's just the fact that this guy will converge to this stationary distribution on graphs where you have, again, to be careful to mean. So there are two things. You have to be careful, what do you mean here, right? So what's the topology on graphs, what's this nonsense? Well, the idea is always that for all of these graphs that you have at any time t, you are always allowed to do some cutoff that says, well, let's get rid of all the edges of weight smaller than epsilon. Okay? This way you have a graph that is locally finite, and okay, and then you want, when epsilon is small enough, anyway, this graph will still have infinite connected components. You have ergodicity property, so you're able to choose a point in that graph at random, so you'll be able to root it in a sort of intrinsic way. And then, well, if once you have rooted graphs, even with weights, it sort of makes sense to see what happens. Ideologically, the topology on graphs you want to use is just saying two graphs are the same if, or pretty close if, when you sample the FK percolation model on them, then you get pretty much the same realization. That's basically the ideology. But here, in that setting, what you see is we have an extremely simple Markov chain defined on an abstract space of graphs. It's not, right, just, and what you see here is if I start with any two-dimensional graph, critical graph with weights, you just let this Markov chain evolve and you converge to the stationary distribution, which is describing you some object that is very closely related, of course, to the critical FK model that shares many features. If you would know this object here, from this object you can read off all the critical exponents and actually work out what the critical object actually is. The critical scaling limit is what the discrete. Okay, so you can retro-engineer and say this stationary measure is actually sort of a measure on d-dimensional type. So let me just say that this stationary distribution, right, is a measure on graphs that is still pretty close to a d-dimensional graph, because the stationary picture is still, you have the clusters that are slightly subcritical, and you're just looking at the respective location of these clusters, and therefore this graph is sort of, in some sense, d-dimensional. Okay. So the property that all these graphs have, if you start here with sort of a transitive graph in d-dimension that you can embed into d-dimensional space in a transitive way, say, then by definition, this one will have also the same property. That there's a natural way to embed, as long as the clusters are finite, you can always, in each cluster, choose a point, say the lowest left point in that point, and this will give you a way to embed this graph in the d-dimensional space in a sort of transitive ergodic way. What these graphs have is that, of course, a given cluster, because you're looking at the scaling limit, has infinitely many neighbors. Right? A given site has infinitely many neighbors, but the sum of the edge weights with respect to all these neighbors will still always remain finite. Okay, so you are always allowed to do the cutoff by that sort of get rid of the small edges, do sample your FK model on there, and then lift back to let epsilon go to 0 and have the scaling limit there. Okay, so I have to be careful with time now. Okay, so what do we get here from this formalism? Well, the first thing is it's pretty robust because it works in any dimension. there's no question about how to embed these graph G. It's just the idea. So the conjecture would be there exists on the space. I'm not going to write, but on the space of graphs G that have the property that there exists a way to embed them in D dimensions in a transitive way. So we are looking at random graphs, okay, that have the property that there exists a recipe to embed them in D dimensions in some way that you can shift the picture you have, and this picture is going to be invariant under translation in ZD. With the feature that the sum of the edges, neighboring edges, given site is finite and things like that. That there exists a unique probability of measure on such D-dimensional graphs that is invariant under this simple Markov chain. Okay. And that basically, if you start with any critical model, say, you start with initial value G0 being Z squared, G0 being a triangular graph, with a well-chosen weight given by PC, it should converge to this unique scaling limit. And for that thing, the convergence will take place, locally will be sort of basically exponentially fast, right? Because the scaling is sort of giving you, you are rescaling at yes?
Could you comment a bit more what prevents this chain of collapsing to something which is not in your space, as it would be if we are below criticality, for instance?
Well, I'm not proving anything. What we know, right, is that for those models, right, where we know that there is a scaling limit and where we can construct what you get, right, I'm not proving. This formalism just says, oh, okay, in those cases where we can control the scaling limit by other means, so this means two-dimensional critical easing, two-dimensional critical percolation on this particular lattice, then we can make sense of the fact that this converges to this given stationary measure, and in the cases where we have universality given by the fact, the description by SLE and so on, then you can say, well, they all converge to the same guy in this class of, I don't know, isoradial critical easing model or something. It just happens that they converge to the same thing. And the big conjecture now can be just reformulated in a sort of softer way, in a way that at least I feel more confident about what is going on, is that for this Markov chain on this big space of graphs that have the property, this sort of D-dimensional property, there's a unique fixed point. And this fixed point is basically, either you converge to something where all the edge weights goes to 0, that means that's the one aspect of the fixed point, or you converge to the thing where everybody, there's an infinite cluster and C either goes to infinity or to 0, or you converge to this stationary guy. And indeed, you have still increasingness in P, right? In the sort of, you still have a phase transition in the yes?
For the very high dimension, there you should still have a piece of scaling working.
Exactly. So I'm not saying, I'm not in high dimensions where there's a discontinuity in the phase, or even in two-dimension Q sufficiently large, then basically there should be no stationary measure there, and therefore you should get this. What I believe is that in this space, it's not such a bad space. So, the idea to shoot for subsequential limits is not completely, out of touch. That's one remark I want to say. The nice feature of this formalism is that indeed, it shows that this sort of renormalization idea is not dimensional dependent. Right? So the general philosophy, this framework works in any dimension. And indeed, in the case of 2 dimensions, okay, we can actually prove things because we know how to prove things by other means. So this doesn't help you to prove anything. But at least it gives also some sort of feeling of, what sort of fixed point in what space you might look for. And there's one important comment I want to make because it might be relevant to some of the lectures later. So what you see here is that you have a natural measure on graphs with weights, right? Sort of in 2 dimensions, you might want to embed them, and you have planar maps with there's some natural objects with weights that is really canonical for each of these models. That's one remark. The other remark is say, okay, now I have this graph G. It lives in some abstract space, which is pretty weird. You don't really know how to. First, you need to sample a point, and it's always defined up to plenty of groups of how to embed them actually in d dimensions. However, the important feature is that these graphs, right, all these graphs, they have a natural intrinsic scale, which tells them the large clusters will look like, or roughly speaking, like a structure that looks like a d-dimensional random but still fairly regular lattice. And the question is, okay, so if I see the random graph and it's not embedded, because the philosophy is just get rid of the geometric embedding, it's just a parasite for understanding what's going on. The only relevant thing is just one piece of information, is just this number of outgoing edges that go out from the connected component. How is there an intrinsic natural way to actually embed it into the d-dimensional plane? And the feature is basically that because this guy is stationary, if you are at the stationary point, imagine you're looking at the 2 dimensions, right, to do it. If you are at the critical point, and then you let the movie run backward at the stationary point, right? So you just look at, at stationarity, you look backwards from where you might have come from. So you choose at random a configuration of smaller clusters that actually did coalesce into this stuff that you look at. And you let it run further and further and further and further. What you see there, right, is this sort of d-dimensional structure that becomes closer, it's a bit like finer mesh in the sort of way in which you're going to embed it. And therefore, it gives you by running the movie infinitely backwards, it gives you actually concrete way by identifying at very small scale your lattice to a regular lattice. You can have your natural way to embed it into the actual 2-dimensional space. So what this seems to, the natural thing that you get, that seems to, path that you go when you go this way, say, well, when I have these guys, there's the way to embed them into the actual physical d-dimensional space will actually be random. I mean, natural random way. When you have the graph with weights, there's a natural random way to embed them in space. And this random way would have actually the property that this embedding is stationary as well, right? So when you do choose this embedding, then you have indeed the near critical, picture as we like to see it, like Gabor, Oded, and Christophe showed in the case of percolation, that you really have the d-dimensional movies with coalescing clusters that actually you can see with your bare eyes, and these growing multi-scale phenomenon that is actually going on. And here, in some sense, you can recover the embedding by looking infinitely backwards in time and see, do the embedding there and see to what cluster you correspond to when you have that. This is very vague, right? So a lot of what I did is was hand waving. But however, the philosophy is, if you want to just take back one message, is there's a very simple framework acting on weighted graphs where you get rid of the geometry, you just get rid of the embedding. It's just abstract Markov chain and graphs for which you can say, well, indeed, I start with a discrete graph. I let it evolve. I converge with a stationary distribution that lives in some continuous space that corresponds to, is still on discrete, almost discrete graph with weights, but still it captures the essential, all features of the continuum model that you are looking for. And we can't prove anything new beyond the fact that, if there's a way to describe scaling, control scaling by other means, then you can plug it into that formalism and say, yeah, okay, now indeed it makes sense. The conjecture is for any 3-dimensional graph, I mean, there's a unique measure on 3-dimensional graph that should be the scaling limit of critical Ising model in 3 dimensions. And it's unique, and it has all the information that exponents that's hidden there. Okay? So there are basically, as I said, 3 models for which we can handle things. The first one is Bernoulli percolation of the triangular lattice. And if you read Christophe, Gabor, and Oded's paper on near critical percolation, and you put these glasses on with this thing, you say, well, okay, there's nothing to do beyond saying they did everything, so that it's just a reformulation of what they did. is saying, well, you know, when you approach the critical point, you have these clusters merging, you have this near critical movie, and you have therefore the critical, the stationary distribution that they have described. So here you need exactly these pivotals. The 4 arm exponents are going to be relevant there. There's the case of the uniform spanning tree, right, that Laura is going to talk about, and where the situation is a bit, as I said, sort of somewhat different, and where actually sort of one can do more or less whatever, you know, in 2 dimensions. Things look pretty good because we can prove that any discrete lattice for which random Moore converges to Brownian motion will converge to the same scaling limit in some appropriate space, and therefore from there you can extract. There's a substantial amount of work that one has to use. Just as keyword for those of you who know, you need to use results like what Greg and Frederick and other people are writing up about, that the scaling limit of length of loop arrays random walk is actually indeed the Minkowski content of SLE2. You need to control in a very fine way the scaling limit, because you need to control these number of pivotals here. So it's not a piece of cake, but one can still make this program work. And of course, easing on number of 2-dimensional lattices is now under good control and should fit as well in that framework. Okay, I'm out of time, and apologize if I was a bit too hand-waving, but I hope was still understandable. Thank you.
Well, let's take questions.
You said that if you look at the invariant distribution, you could read off the critical exponents. But I mean, if you look in, for instance, this near critical percolation, you still have more information because you also have the geometry of the clusters, which here you completely lose, right? Because you collapse them to a point.
Yes.
Is it obvious that you can?
No, I mean it's not obvious. Well, I mean I was going. I mean basically what I was trying to say with this thing, that you have this space of graph, and it has this sort of ergodic, it has this ergodicity built in, and it is stationary. So by looking at this dynamics there, you can sort of roughly, you say, well, okay, on large enough scale, this graph is sort of fairly, I can embed it in a way that is fairly regular and d-dimensional, and therefore I continue to let it evolve, and then you see sort of, it's not really eigen. I mean, you could add, you could decorate this thing by adding other, information. Say when 2 clusters merge, there's some object, the mass. Say, you can look at what happens to the mass. You can look at what happens, and then you'll see that the number of points on clusters can control it, sort of, and it will naturally, increase exponentially at a certain rate, and this will start giving you information, about, how many points there are in each of the clusters, things like that. So,
but it's not trivially. You can't read it trivially. That's what.
No. But if you dig it enough, you will be able to find, extrapolate from. I mean, this. Yeah, that's it. Yeah.
So have you? Have you thought about whether there's any way to describe this scaling limit graph rigorously, completely, without using SLE? There's some power law on the sizes of these components. They're distributed in some way with some.
So the answer short is yes. I have thought about it. I mean, there's no. Because geometry, you kick it out and then comes back from the window, because you want to have your this stationary measure is, you need to make sense of what it means to be d-dimensional, right? Because you know that's just 1 in 3 dimensions, 1 in 2, and so on. So you are still sort of looking at graphs that have some flavor of d-dimensionality, and so if you just kick it out, say, let's do a bit, planar quantum gravity type approach by saying, don't care, we explore things in a dynamic way, and we add, weights according to a stable, I don't know, whatever. I don't see sort of not a simple way to do that that framework. So, but yeah, I mean, I thought that might be a good idea to throw this model here because maybe some of you have some natural ideas of how to move from there. Yeah.
Just continue. So, do you think there's any chance of trying to just abstractly say that, look at which are the invariant distributions, and then say, well, we can, I mean, just abstractly find them, because that's what I would expect, that you find a certain number of these abstractly, and then you say, oh, look, just one that looks two-dimensional. Well, there's going to be one for every dimension where you have a continuous space. Then maybe they're on trees or it's something else. I mean, you should.
Yes, I fully agree. I mean, that's sort of the natural candidate one wants to do, but of course it's sort of a, if you're living on trees or something, that's not exactly what we're shooting for, right? We want to shoot for understanding these. I'm not so super optimistic about the fact that there will be, a very easy way to construct a stationary distribution just out of, homework exercise for next week. Construct me a way to construct a stationary distribution using, power laws. Because if you look at it's very simple, the Markov process. But it's not that simple because you need to simulate. I mean, you still need to sample the AFK model on the infinite graph in order to know at what rate these things are going to collapse. So it's not, So it may be okay if you're in a tree. Then anyway, FK population, everything's the same. And so indeed, but as soon as you get the loops, they really, come into the game, and it's hard to get rid of the geometry that arises when you look at the dynamics of the process.
Now, you mentioned there might be a quantum gravity version of this.
I didn't mention. I just said. That's a question for you.
Will that be easier, maybe?
Huh?
You think that will be easier?
That's you guys. My team can tell me. It's a natural question. I have no intuition about it. I don't see a particularly easy way to do it. In some sense, here really you're, don't know.
I didn't quite understand how the embedding works. Reading it back. I don't want you to explain it again, but just a question about it.
No, I mean.
So do you think you can read off from this what the right embedding for different models is to get, like, for percolation, if you have some non-standard lattice,
Yes.
is circle packing or something is the right embedding to get conformal invariance?
Well, I mean,
Voices.
no, I mean the message here is that what this seems to indicate is that the embedding is random. So, I mean, the way you're going to get the embedding from this recipe is not going to tell you, this beautiful, circle packing or, aesthetically pleasing, and that the one we really want is going to come out of this. No way. I mean, what's going to come out of here is just the fact that there will be, I give you this abstract graph, there will be a way to embed it which is actually random, because it comes really out of the dynamics running backward, which have some randomness in it. So, but I think this is some general philosophy that, after all, why once you start playing with graphs which have weights and you have also all these things that are, how are you going to, I mean, just to start with, I mean, just as I mentioned, the graph has typically at criticality you have a picture like that, right? This is how two clusters touch. So now we're saying this guy is connected with this guy, and there's just one edge between them. Right? And here you have all these guys here, these smaller things. And so in G, you don't know who's on what side. How is this chain here or there, or how's the generic structure, you can then try to recover it, because then you say, well, there's no way to get out. But you have to work a little bit, and still there's some there's some room for quite a lot of random things going on. So obviously, and therefore you will be So it's not really the graph G you have here. There's no natural, unique embedding as a planar graph. Precisely, you have these things here, so it's a bit weird.
Yeah, let's